Hi, I'm Adam. This is the Machine Tech video blog, and today I'm going to continue our discussion on autocollimators. In the previous video, I described, in a very general sense, how autocollimators work, including why they are only sensitive to angular changes in a mirror and why that's so useful. I also casually mentioned that based on the focal length of the objective lens in the autocollimator, as well as on the resolution of the scale and the magnification of the eyepiece, both of which have to do with sensing the movement of the return image of the crosshair, you can tell exactly what the angular change of that mirror is, very, very precisely. In this video, we're going to explore those relationships further, which means we're going to have to dig even deeper into optics and the related math. But don't worry, I'm going to try to cover this as intuitively as I possibly can, and luckily, all of the parameters I just described are related through a very simple formula, the Autocollimator Formula. And here it is in all its glory. D equals 2 times theta times f sub L, where d equals the linear displacement of the crosshair image in the eyepiece, and this can be inches, millimeters, angstroms, whatever you want, as long as you keep it consistent. Theta is the angular change of the mirror, and that's in radians, okay, so you have to be careful about that. And f sub L equals the focal length of the objective lens, so that is a fixed value that just has to do with the autocollimator's design. I told you that it was simple, right? Now the thing is, this formula is not super descriptive of what's really going on in the optical system. So let me take out that optics discovery kit that I used in the previous video to illustrate some of these points by recreating this setup. So let me describe what's going on. We've got a point light source represented by a light bulb, which is positioned at the focal point of this lens. So that's on the optical center of the lens, on the focal plane, which is distanced 1 focal length from the lens. Okay, I'm going to turn this light source back on, but what I want you to do is imagine that these light rays coming from this light source are actually these light rays coming from the point source, but reflected off of a mirror. So what we can see here is that if our hypothetical mirror is perfectly flat and perfectly perpendicular to the optical axis of these light rays, then the light is perfectly reflected back into the lens and it just reconverges at that focal point, right on the light source. But what will happen when we take our hypothetical mirror and change its angle? And here we go. All right, and now that is pretty interesting. Notice that all the return rays converge at a point which is on the same focal plane as the point light source. So the focal plane hasn't changed. But what has changed is that this focus point of the return rays has been displaced down a little bit from where the point light source is. So let me draw in a few more things here, and I think the whole picture will come together. So the change in angle of the mirror from where it was before, which was perfectly perpendicular to the optical axis, is theta. And the displacement, the change in position, this linear distance right here, from where the focal point of the return rays is now to where it was before the angle of the mirror was changed, is d. Now, I think that that is really, really cool, and it's a great visual representation of the relationships in this mathematical formula. But it still leaves some unanswered questions in my mind, like, why is it 2 theta, and where does this focal length come from? First, let's address this 2 theta business, and I'm going to do that with the integrated circle chart that came with the optics kit that I bought. It's marked out in increments of 15 degrees, and I think this little experiment is going to shed some light on the matter. I have a little reflector here, a mirror, which I'm going to place in the center of the circle chart. Then I'm going to turn this one laser on and turn off the light so that we can see what's going on. Right now, the light ray is coming in at 0 degrees, and the mirror is at 90 degrees. So this reflector is perpendicular to the incoming light ray, and so right now the light ray is being reflected back to its source. You can't really see it that well, but if I wiggle it a little bit, you can see that it is returning to the source over here. Now let me rotate the angle of the mirror to 15 degrees. 15 degrees. Okay, so this should be pretty straightforward. The angle of the mirror relative to the incoming light ray is 15 degrees, so the angle of the reflected light ray should also be, wait, 30 degrees. What the fuck? There's something going on here. I think this is going to be easier to visualize if I keep the mirror at 0 degrees and I change the angle of the light source. All right, now we can see the relationship. So the incoming light ray, which is called the incident ray, is at 15 degrees relative to the 0 line, which is perpendicular to the flat plane of the mirror. The 0 line in this case is called the normal line relative to the reflector. But this light ray, which is bouncing off of the mirror and is called the reflective ray, is also at 15 degrees relative to the normal line. Both the incident and the reflected light rays have exactly the same angle relative to the normal line, which is perpendicular to the reflective surface. That means that the total angle between the two light rays is always going to be exactly twice whatever their angle is to the reflective surface. This relationship is so important in optics that it has its own law called the law of reflection. What this means for us and our quest to understand the inner workings of autocollimators is that collimated light coming out of the autocollimator will be reflected back into the autocollimator at exactly twice the angle of the mirror relative to the collimated rays. If the angle of the mirror is at 15 degrees, then the angle of the reflected ray will be 30 degrees. And if the angle of the mirror is 30 degrees, then the angle of the reflected ray will be 60 degrees, and so on. Okay, I hope that that clears up the 2 theta issue, but now we have to talk about lens focal length. I've already talked quite a bit about focal length. Focal length is the distance from a converging lens at which light rays coming from infinity, that is collimated light rays, will focus on the other side of the lens. This is a real, physical, linear distance which can be measured and quantified. That's the focal length of a lens. Now, I say a lens because different lenses can have different focal lengths, different distances from the lens at which they bring converging light rays into focus. And actually, this is the most important parameter of a lens. Everything else is sort of secondary. I've got some lenses here that I'm going to use to demonstrate lens focal length and a few other related concepts. By the way, these come in these inexpensive educational kits that have a bunch of different lenses with different focal lengths in them. These are a great way to do simple experiments and learn about basic optics. I've got 3 lenses here, all of which have the same diameter, which is 50 millimeters, just under 2 inches. But each one of them has a different focal length. This is 20 centimeters or 200 millimeters. This is 30 centimeters or 300 millimeters. And this is 500 centimeters or 500 millimeters. So this lens will bring incoming parallel rays to a focus at a distance about twice that of these 2 lenses. I'll show you what that means in just a moment, but first let me show you something about these lenses. Now, I don't know how well you can make this out in the image, but if you look at the side profile of the lenses, you can see their curvature. And notice that the curvature for the 3 lenses is different. So on the far left side, that's the 200 millimeter focal length lens. That's the shortest focal length that I have out of these 3 lenses. And on the far left is the 500 millimeter focal length lens. That's the longest focal length that I have here. And notice that the lens with the shortest focal length has the most curvature, meaning that it has a relatively small radius of curvature. And notice also that the lens with the longest focal length has the least curvature. It has a relatively large radius of curvature. In fact, this is approximating more and more a flat plane, which you can kind of think of as a curvature of infinite radius. So what this shows is that the curvature of the lens determines its focal length. This relationship probably isn't that surprising to you, that a smaller radius of curvature means a shorter focal length, and a larger radius of curvature means a longer focal length. It's sort of intuitive that the more a lens curves, the more sharply it bends light, and therefore the light rays will converge at a shorter distance from the lens, and vice versa. It's important to note that the focal length of a lens is specified when the incoming light rays are perfectly parallel to one another. This is usually accomplished by pointing the lens at a light source which is so far away that it can be considered infinitely distant. This object might generate its own light, for example a star, which is so far away that it can be considered infinitely distant, and it generates its own light. But it also might be an object which reflects light generated from other objects. For example, the moon does not generate its own light, but it reflects light from the sun, and it's far enough away to be considered infinitely distant. But these don't have to be celestial objects. They could be much, much closer to home. And in fact, what's considered infinitely far away depends a lot on the focal length of the lens that we're talking about, okay? So to demonstrate this and a few other points, I'm going to pack up my lenses and go on a field trip. I've come out to the Port of Oakland to do a little experiment where I test these educational lenses. I have this white piece of paper taped to a 246 block, and this is going to be acting like a focal plane, okay? And then I've got this ruler, and between all of these components, I should be able to find out exactly at what distance from the lens this focus plane needs to be in order to produce a sharp image of an object which is far enough away from the lens to be considered infinitely far away. They say something like 10 times the focal length of the lens ought to be good enough. That's what I'm going to be focusing on. Those are some cranes for shipping containers at the Port of Oakland, and they are for sure far enough away to be considered infinitely distant. Since it's a really, really bright day out, I'm going to have to cover everything with this cardboard box so that any stray light can be eliminated. You really need to do this for, best performance. You need to do this inside of a dark, enclosed environment. So there it is. You can see the image on the piece of paper, and I think that's pretty cool. The piece of paper is positioned at a distance from the lens at which light rays coming from infinity are converged to their sharpest focus. That is to say that the piece of paper is at the focal length of this lens. Notice also that the image is inverted and reversed. That's a thing that happens with simple optics. So the distance between the lens and the piece of paper at which the image is at its sharpest focus is, well, looks like just under 8 inches. And that makes sense, right? Because the nominal focal length of this lens is 200 millimeters, which is like 7.87 something inches. So this follows. Okay, now let's try the same thing with this lens, which is the 500 millimeter focal length lens. All right, there we go. That's the sharpest image that I was able to form. Now I want you to notice a couple of things. One is that obviously the piece of paper is significantly further away from the lens this time, but also the image is magnified, and that is important. And now if we look at the ruler, we'll see that the distance between the lens and the paper at which the sharpest image forms is more like 19.5 or something like that, which makes sense because this is a nominal 500 millimeter focal length lens, and that's about 19.68 inches. So again, this follows. What do you think about that? Pretty cool, right? And if we replaced this paper with a piece of photosensitive film, then we would have had ourselves a camera. Not a very good one, but yeah, that's basically what it is. I think that was a pretty clear demonstration of lens focal length, but it may take a little leap of logic to understand how that's related to autocollimators. I mean, we're comparing an imaging system to the autocollimator system, and actually an autocollimator is an imaging system, even though you may not have thought of it that way, and all of the same principles apply and all of the same behaviors are shared. The most important consideration for our current discussion of autocollimators, and the one that has to do with focal length, is that long focal length lenses not only form sharp images at a greater distance from the lens, but the images that they form are enlarged or magnified. Maybe an intuitive way to think about this is that the further the light travels before it's focused, the more it spreads out. That's kind of what's going on. It actually has to do with the light gathering capabilities of the lens and its angle of view. But the point here is that the same reason why a lens will produce a magnified or enlarged image is the reason why the displacement of the return image in an autocollimator system will be larger for the same angle if the focal length of the lens is longer. Going back to the Autocollimator formula, we can see now that the displacement is equal to twice the angle of the mirror, which we already explained, times the focal length of the lens. So this is a nice linear relationship, where if you have, let's say, a 150 millimeter focal length lens, the displacement will be exactly half that of a 300 millimeter focal length lens for the same angle of tilt on the mirror. I hope that that makes sense. I'm trying to explain some really important concepts in optics without getting too much into the weeds, so I've done some simplification here and I hope that you followed. For me, at least, it's really useful to understand where formulas come from instead of just memorizing them, and that's what I've tried to impart upon you here. But enough theory. Let's put all of this knowledge to work for us with a practical example. Remember this thing? This is the Davidson Optronics D657 autocollimator, which I walked through in the previous video. Now, this was an eBay purchase, and I didn't get a manual with it, and the company has obsoleted this product, so they won't even give me the time of day. So, to be really honest with you, I don't actually know what the sensitivity of this instrument is. But, using the Autocollimator formula, I can figure that out pretty easily. Let me show you how. The focal length is an easy one. That's just the distance from the objective lens to the crosshair reticle, and I bet that I can measure that just with the measuring tape. So, okay, I'm going to assume that they used some nominal inch size and call this 5 inches focal length. For the displacement, I'm going to use 1 division on the scale in the eyepiece, because even though you can interpolate between divisions, 1 division is really the minimum resolvable value here. And then I'm going to solve for theta, because that's going to tell me the smallest angle of tilt on the mirror that this autocollimator can resolve. You know? I don't think I'm going to be able to measure that with the measuring tape. So in order to measure 1 division, I'm going to have to take another field trip. Hey folks, so I'm here at the college, which is where I keep my microscope, my beloved Nikon Optiphot, right next to a model D309L plano interferometer, which is another very, very cool Davidson Optronics device, but that's definitely another video. So let me go ahead and show you how I have this thing set up. So I've got the autocollimator set up on the microscope stage. This is an XY stage, so it will translate in both X and Y from the current vantage point of the camera. That's forward and backward and left and right. Okay, I've removed the eyepiece from the autocollimator, and I've got this 5 times magnification objective lens focused on the scale. And then I have this mirrorless camera set up at the end of a photo tube so I can digitally record the image in the microscope. So you can see the scale right there. I'll actually switch over to this footage in just a moment. But let me talk briefly about how I'm going to check the spacing between the graduations. I've got this indicator set up on the side of the stage so that when I translate it in this direction, I'll be able to read that movement. This indicator is a tenths reading indicator. Each graduation is a 1/10 of a thousandth of an inch, and I think that resolution is going to be appropriate for what I'm trying to measure here. So here's what it looks like inside of the camera, and you can see the blown up image of the scale. And the idea is to find one of those graduations and then zero out the dial indicator and then move the stage to the next graduation. and then read that distance on the indicator. So that's 0, 1, 2, almost 3, so 0.029. Now, that seems like a kind of like a random number, but let's plug it in and see what we come out with. By the way, what I basically did here was convert this research microscope into a toolmaker's microscope by putting a fine resolution readout on it. This actually does have a scale on it here on the side of the stage, but it's not nearly close enough resolution for what I needed. A toolmaker's microscope might have like a digital readout or micrometer heads on it, but you know, this works in a pinch. Okay, so for the displacement, we're going to use 1 division, which came out to 0.0029 or 0.009, and we want to solve for theta, so I've rewritten the formula to solve for theta. So 0.0029 divided by 2 times 5 is 0.00029. Now that number may look very weird to you because this angle is in radians, so we still need to convert this over to degrees. The conversion is multiply radians by 180 over pi and you get 0.0166 degrees. Now that still seems like a pretty random number, so let's convert this decimal degree into degrees, minutes, and seconds. So to get from decimal degrees to arc seconds, you multiply by 3600, and the result is 59.796 arc seconds, which is very, very close to 60 seconds or 1 arc minute. So factoring in a little bit of uncertainty in my measurements, I think it's reasonable to assume that the intended resolution of this autocollimator is 1 arc minute per division. You know, when I told you that I didn't have the manual for this autocollimator, that was technically true, but it was a little bit of a white lie because I do have the catalog. This is actually a fantastic catalog filled with all manner of fascinating devices, none of which are sold anymore, but many of which can be had on the used market if you keep your eye out, and if you're interested in that kind of thing. But immediately relevant to us is this page on the D657 tooling autocollimator. It's called a tooling autocollimator because it was simple and inexpensive enough to be integrated permanently into whatever device you were designing. But the important piece is right here under reticle accuracy that the graduations are 1 minute increments. And over here, the focal length is 5 inches. So there you go. So I could have just looked in the catalog, but I think it's really cool that you can also check it the other way using the Autocollimator formula. Whoa, that was a lot of information. And actually, there were some things which I mentioned in the previous video which I didn't cover in this one. Specifically, how to convert the tilt angle of a mirror into a vertical change in height when you're evaluating flat surfaces. But that was actually on purpose because I think that that will be better covered in separate videos on testing and using autocollimators. Everything I covered in this video is really important to understand how autocollimators do what they do. But there are actually a few more subtle nuances to consider when we're talking about designing a real working autocollimator, which is what I'm going to talk about in the next video. I'll be discussing the selection of optical components and going through a few different autocollimator designs, from the very simple to the much more complex. But I'm going to end it here for this video. So that's it from the Machine Tech video blog. I hope you learned something.